Hello again, Physics 243. This unit will discuss the way musical instruments works, in particular pipes and strings. Maybe I should say strings and pipes because we'll mention strings first. Actually, we've already done strings. So remember that at the end of last unit, we were talking about standing waves that you can set up on a string. You can have something like this and like this and like that. This one is called the fundamental, right? The first harmonic. We calculated its frequency, but let's just call it F1 here. The next one is the first overtone or the second harmonic. It has a frequency that's twice as much as the fundamental. And this one, which is the second overtone or the third harmonic, is 3 times the frequency of the fundamental. So it's called the second harmonic because it's twice as much as the fundamental frequency, and the third harmonic because it's 3 times as much. Alternatively, the naming scheme is fundamental, first overtone, second overtone. Okay, so we did that already. Now, what's interesting is to talk about pipes. So sound can be produced in a vibrating column of air in a tube or a pipe. And this works for tubes that are closed at one end or open at both ends. All right, so I want to show you this. So let's, hello. I've got a couple of things here. Here's a bottle. And I can play the bottle. Right, so that's the basic phenomenon that we're going to be talking about just now. We have a column of air, and I blow across the top. So what happens is I blow across this edge, and there's an instability, and the air starts going in and out, in and out, in and out, in and out. And that causes the air in here to vibrate. And we'll talk about the modes in which it can vibrate. That's basically what's happening. You can use different bottles. Here's another bottle that's shaped a little differently. A different sound. Here's a wine bottle. This was a nice Riesling I had the other day. It's bigger, so quite a lower sound. And one time I went to Peru and I got this. So these are sort of wooden pipes that are closed at one end, see? So similar to these bottles, and you can play them. Okay, so I can't play it very well. But one thing that's interesting about this is that so far I've only excited one mode of oscillation of the air column. And there are higher modes, just like in the string. You could have the fundamental, and then you could have higher, more complicated, higher excitations of the vibrations. So I'm going to play this long one here, which is closed at this end and open at this end. Okay, now if I blow harder, I can excite a higher mode of oscillation. Hear that? You can also do that with a bottle. It's harder though. It's fundamental. You hear that? There's one of the overtones. And in principle, you can get even higher ones, but it's practically impossible to do. All right, so those were basically tubes, bottles, pipes that are closed at one end. You can also do this with one that's open at both ends, except that it's hard to make it sound nice or reasonable or like an actual tone. But you can get the sound of it. There's a particular tone there, right? Okay, we'll come back to this one later. All right, let's go back to the PowerPoint. Here we are. All right. So yeah, sound is produced by vibrating columns of air in these different kinds of tubes. Hello, there we go. All right, let's start talking about a tube that's open at both ends. Okay, so how does the air vibrate in a standing wave kind of a mode? So there are these pictures that the book shows you, and it's important to talk about what they mean because it's a little confusing. The blue is the walls of the pipe. So you're looking at a cross section of the pipe, and the blue are the walls of it. So, it's closed in a semicircle in front of you coming out of the screen and a semicircle going on the other side of the screen. And you're looking at a slice through the middle. and it's filled with air. And what happens is, here are the motions of the molecules here. Right? In this lowest mode of oscillation, this fundamental mode of oscillation, what can happen is that these molecules on this end go back and forth. These end go back and forth as well, and the ones in the middle stay still. Importantly, if this one is going to the right, if all of these here are going to the right, then at the same time, these are going to the left. So I want to show you. Okay, so the air is doing this basically. Right, there's the tube, and the molecules are going back and forth like that, and the ones in the middle are not moving at all. That's what I wanted to show you. Go back. All right. Now, these lines, this sort of magenta and this orange line, are ways to depict that. So these curves represent the displacement of the air molecules at times half a period apart. Okay, so you might say that this value, let's look at this red one here, magenta one. This is high. That means that this particle is moving to the right. And this one's moving to the right, but not quite as much. And this one's moving to the right, not quite as much. And then it's stopped here. Then we come over here, these guys are moving to the left, to the left, to the left. So when it's below the midline, it means it's moving to the left. When it's above the midline, it's moving to the right. Now, a half period later, these guys have reversed. These guys are now going to the left. And so we have this orange curve. Left, 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 and then right, 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 right. Okay, so as these guys go back and forth, you can imagine that this magenta one switches to this orange one and then goes back to the magenta one and goes back and forth like that. And that's just a way to represent this motion, this actual motion of the air molecules. All right, the ones in the middle don't move. So that's the meaning of this. Okay, and we have a pipe of length L. A couple comments. A node, this node here is where the molecules don't move, just like that one. And the open ends must be antinodes, so the air can move in and out there. It's free to do so. So in this mode of oscillation, it has to do that. Excuse me. And then the fundamental mode has one node in the middle like this. The book shows you pictures that also look like this. So in this case, what's depicted by the lines is pressure variation. So the same standing wave as shown here can be described in terms of pressure. So in this case, you have high pressure in the middle, switching to low pressure, to high pressure, to low pressure. Right? You can imagine that as these molecules of the side move towards the middle, you're increasing the pressure there. And then as they move away from the middle, you decrease the pressure there. And at the ends of the pipe, the pressure has to be fixed because it's open to the atmosphere. Okay. So this is the same phenomenon, just depicted in two different ways. This one shows you the motion of the particles. These lines represent the motion of the particles back and forth. And in this diagram, it shows you the pressure variation on the inside. Same phenomenon, different ways of showing it. I'm going to stick with this one. So never mind this kind of description in terms of pressure. Let's talk about this one. So I'm going to draw pictures that look like this. Okay, so we're considering a tube open at both ends, and this is the fundamental mode of oscillation. Right, the molecules here move back and forth, these move back and forth, and the ones in the middle don't. That's the fundamental frequency. Now let's figure out the wavelength. So if you look at this, that's not a full wavelength. You have to sort of make a copy of the pipe so that you can see an entire wavelength like that. Right, so I sort of copied it over and flipped it upside down. In order to see that one wavelength is twice the length of the pipe. So the wavelength for the first harmonic, the fundamental oscillation, is actually twice as long as the pipe is. Right, what you see here is half of the wavelength. Okay, so we know this wavelength now. Let's remember this relationship, that the speed of a wave equals the wavelength times the frequency. If we solve that for the frequency, we have the frequency equals the speed of the wave divided by the wavelength. So in this case, the V represents the speed of sound in the air, And we can write down the frequency by plugging in this wavelength. So the fundamental frequency is the speed of sound divided by twice the length of the pipe. Okay? So we'll hold on to that result. That's the frequency of the fundamental. Now here's the second harmonic, or the first overtone. It's a mode of oscillation in which there are two nodes. And so here, the molecules don't move. Here, the molecules don't move. Here, they move back and forth. Here, they move back and forth. And here, they move back and forth. So I see it's a higher excitation, higher mode of oscillation, as it were. Okay, let's try to figure out what a wavelength looks like. And you can actually see an entire wavelength here. So in this case, the wavelength is the same as the length of the pipe. Right? So the wavelength of the second harmonic is equal to the length of the pipe, lambda 2 equals L. And if we plug that into this relationship down here, we get that the frequency of the second harmonic is V over L, which is twice the fundamental frequency. Okay, so that's, I've written now F2 in terms of this F1. All right, so it's kind of interesting. Now let's talk about the third harmonic. This one gets a little more complicated. So now we have three nodes, right? Node, node, and node, where the air doesn't move, doesn't move, doesn't move. And in between, the air moves, back and forth. And that's the third harmonic of the second overtone. Let's think about what a wavelength is in this case. So let's draw the picture like this. And you can see a wavelength like that. How is that distance related to the length of the pipe? Well, what we can do is we can divide up the pipe into thirds like this. So draw a line where these antinodes are. And we've divided the length of the pipe into 3. And notice that one wavelength is 2 of these thirds. There's one wavelength. And just by looking at this, you see that the wavelength of this third harmonic is 2/3 of the length of the pipe. There's one wavelength. Or you can look at this one, and that's one wavelength. Okay. So once again, let's plug that into this. Frequency is the speed over the wavelength. So V divided by that wavelength, 2L over 3, which can be written like this. And remembering that the fundamental frequency was this V over 2L, we see that this is 3 times the fundamental frequency. Okay, so we have this result. And in principle, this continues forever, although practically it's very hard to excite these higher harmonics, higher overtones. But we have a sequence like this, that the frequency of the nth harmonic, where n equals 1, 2, 3, 4, 5, etc., is n times the fundamental frequency. And that's the result that's just like the string that I showed you. We have the same result for a string. Right? So you could excite the fundamental, and then the higher excitation, higher modes of oscillation are just integer numbers times the frequency of the most fundamental one. All right, so that's the tube that's open at both ends. Let's now consider a tube that's open at only one end. So it's closed at the other, like this. All right, so in this case, here's the motion of the particles of the air. Right, there's a wall here. So the air here can't move back and forth. There's a wall there, right? So these molecules here don't move. We necessarily have a node here. And this part of the pipe is open, so we necessarily have an antinode here. When we have a standing wave, these particles move in and out, back and forth like that. And with less amplitude as you get closer to this node. So that's what, again, that's what these two colors represent. In this case, they're going one way. In this case, they're going the other way. And it flips back and forth. All right, so let's try to figure out the frequency of this fundamental mode of oscillation that we show here. That's the first harmonic. So let's in order to get the frequency, we'll follow the same strategy as before. We'll get the wavelength by basically looking at the pipe. And in this case, here's a copy of the pipe. It's cut off here, but what I'm going to do is make another copy of it. And actually I have to make 4 of them in order to get an entire wavelength. See the magenta starts high, goes low, and then goes back up high. So I need to make 3 extra copies because the wavelength is 4 times the length of the pipe. Right? When you look at the actual pipe itself, we only see 1/4 of the wavelength. And sorry that I couldn't get these things to align quite right. Okay, so if the wavelength is 4 times the length of the pipe, remember this relationship, frequency is the speed of sound divided by the wavelength. So we get that the fundamental frequency of a pipe that's closed on one end is V over 4L. All right, here is the next higher excitation, mode of excitation. Again, we have to have an antinode where the pipe is open, and we have to have a node where it's closed. So here the molecules do not move, and here they move in and out. And we can fit another node in there. So think about how the wavelength of such an oscillation is measured in terms of the length of the pipe. So let's take this orange one. It's down here, it goes up here to there. You would extend it out to here, right? So you could divide it up into this much, and that. So divide this into 3 and then add 1 more third. That would give you a full wavelength. Sorry, I don't have the picture of it, but I think you can work it out. In that case, and this should say lambda 2, excuse me, this should say lambda 2, is 4/3 of L. Divide this into 3 and add 1 more, so you have 4/3 of the length of the pipe. That gives me a frequency of 3/4 V over L, which is 3 times the fundamental frequency. Again, this should say F2, that should say lambda 2. So we went from the fundamental directly to 3 times the fundamental for the next mode of oscillation. And here's the 5th harmonic. And I'll let you puzzle out how much of L one wavelength is from there to there. You'll get that it's 4/5 of L. And that gives us 5 times the fundamental of the frequency. Again, this would be lambda 2, and this should be F2, I guess. And that works out to be 5 times the frequency of the fundamental. Okay, so in principle, that goes on forever. What's the general rule? Well, notice we only get the odd harmonics. Right? Remember, the harmonic is how many times the fundamental frequency. This is 3 times. You can't get an oscillation that has twice the fundamental frequency. It doesn't fit. You're required to have a node here and an antinode at the other end. So you can't get a frequency of twice the fundamental, but you can get all the odd multiples, 3, 5, etc. So there's a general rule. The higher harmonics have a frequency m times the fundamental, where m is an odd number. And so that's different than what we saw for the pipe open at both ends and different from the string. Closed at one end, you only get the odd harmonics. Okay, so let's summarize. Here's the tube open at both ends, and you can learn to draw these pictures like this. The terminology I know is obnoxious. First harmonic, second harmonic, third harmonic. The first harmonic is called a fundamental, and then the next excitation is called a first overtone and a second overtone. So yeah, kind of annoying terminology, sorry about that. The fundamental frequency of oscillation is like this, V over 2L, L is the length of the pipe, and higher harmonics have frequencies like this. For the tube that's open at only one end, fundamental frequency is V over 4L, and higher harmonics occur with only odd multiples of the fundamental frequency. Okay, so looking at this, we can make a prediction. And here it is. So I guess my animation didn't work. If we have a pipe that has both ends open, the fundamental frequency is V over 2L. Let's compare that to the fundamental frequency where the pipe has one end open, which is V over 4L. And factor out a half. What's in parentheses here is F1 with both ends open. So we have this relationship. The fundamental frequency of a pipe with one end open equals 1/2 of the fundamental frequency of a pipe with both ends open. So this leads to a prediction. If you play a tube that's open at both ends, you'll hear a sound, and that'll give you this frequency. Now, if you close the other end and play it, it should sound with a frequency half as much, which corresponds to an octave lower. So half as much frequency is an octave lower. Let's see if it works. Hello again. I have my pipe here that's open at both ends. Where's my eye? There it is. So you see it's open at both ends. And again, it doesn't make a nice clean tone, but you can hear the pitch definitely. Okay. Like that. And now I'm going to put my hand over the end and play it again. Whoops, I didn't do well. Actually, there's a little bit of a opening here. I'm going to put my hands there. There. Okay, put my hand over the other end. Octave lower, right? Here, let me show you what I'm doing. Stand close. There. Okay, open. Like that. Put my hand over the end. Octave lower. So the prediction is right. Okay. So that's what I wanted to cover in this unit. I hope that was entertaining. Next up, we'll do a couple more problem examples and then move on after that. Okay, see you in the next one.